Alright, good evening y'all. My name is Jack McElroy. I've been doing ham radio ever since I was a tot. My dad put me in front of a radio to listen to WWV counting down New Year's back when I was probably 3 or 4. And later on when I was 9 I got my technician license and later my general license. And I've been doing a lot of stuff with ham radio.
Yeah. It's the projector that's keep going.
And so I've done stuff from satellites, so low Earth orbiting satellites, contacting them, talking to astronauts, and using them to talk to people across the world. So a great example of that is using satellites like Green Cube. I ran the satellite station with the Sony Amateur Radio Association, SARA, for the last couple of years, and we've had a great success of that. But along with all of that, I've been launching high altitude balloons, which are a unique conjunction of both amateur radio with traditional weather balloons. And so I'll be sharing with y'all my experience with that and my work with HABs to bring them to youth and to help bring youth into the hobby. So the foundation of amateur radio is STEM: science, technology, engineering, and mathematics. And that's the foundation of high altitude balloons as well. And so radio, it builds upon STEM in many different ways. Low Earth orbiting satellites, LEO satellites I talked to you about previously, those are based upon complex systems, complex telemetry receiving systems, telemetry transmission systems. And if y'all remember, some of y'all might have been around for this, but it was only about 60 years ago that scientists with slide rules, no computers, no calculators, no fancy stuff, were able to put men on the moon only about 50 years after aircraft were invented. So, and along with that, we also have circuit design. So a lot of kids are introduced to engineering, to mathematics, to technology from learning by ham radio. I'm sure many of y'all remember tinkering around with like snap circuits or basic plug-and-play circuits back when you were younger to help build your first transmitter or antenna. And along with that, the biggest use of STEM with ham radio is high altitude balloons, or HABs. So HABs, these are scientific balloons connected to amateur radio, and there's two types. We have latex traditional balloons like the ones you might see on a Nat Geo or National Geographic cover, and then we also have the second type, which are called picoballoons. And as the name suggests, these are small little balloons. And what makes these balloons different from traditional latex balloons is that they're able to float at a predetermined altitude for days, weeks, and sometimes even months at a time without popping, and being able to carry a payload around the globe. And the uses for these balloons are multifaceted. We can use them for scientific research, which is the primary use. Colleges, scientists, professors are able to use cheap balloons to carry their payloads way up into the atmosphere to research the heavens. And in fact, HABs are often called the poor man's space program because they're exactly that. They're a cheap and effective way to allow researchers of all ages to bring the research into the sky without spending tens of thousands of dollars on fancy rockets or other technology. And along with that, there's also radio outreach. So high altitude balloons are something that's familiar to many people. Many kids might remember seeing footage of NASA launching some massive balloon in like Christchurch, New Zealand, or go to any toddler birthday party and you'll see balloons all throughout the place. And so by combining balloons, whether it be normal party balloons or weather balloons, with ham radio, we're able to provide an easy bridge for kids to walk on to be able to connect something that they're familiar with amateur radio. And that way we can bring more kids into the hobby and to keep this hobby alive for many years to come. And finally, the biggest use of these is just fun. You know, kids just like being able to put together their own payload, experiment with amateur radio, and be able to say, I sent something up to the edge of space, or being able to say, here's some footage of my balloon capturing the curvature of the Earth. And so you can do lots of cool stuff with high altitude balloons, and I'll try to describe to you some of those fun things that I've done with them. So the first type of balloons I mentioned before, the traditional HABs, or high altitude balloons. These are the most common balloons that you'll see. And as I mentioned before, these are used a lot by research organizations. So NASA, National Weather Service, Google, as well as many normal balloon enthusiast amateur radio operators. And these essentially work in the principle of being large party balloons. We fill them up with lots of helium or hydrogen, and they float up carrying a large payload until they reach about 80, 90, 100,000 feet, and at that point they pop and fall back down. Now the nice thing about these balloons is that they can carry massive payloads. So typically with my balloons, I can carry payloads of a couple pounds, but if you can catch the picture there, that's the Georgia Tech high altitude ballooning group, which my sister is a part of, and they were able to launch this balloon with about, I think, 12 pounds of equipment on it. And with that, they carried hygrometers, thermometers, biological samples, all kinds of stuff, small amateur radios on board, and with that, they were able to conduct undergraduate research with this fairly cheap system. These balloons usually go to very high altitudes, so we expect them to go to about 90 to 120,000 feet. And at that point, they're starting to you start to see the blackness of space. You see the curvature of the Earth, and you can see probably about a quarter of the globe at that altitude. But these balloons are also designed to be short-lived. So they go up really fast, and in about 3 to 12 hours, depending on the size of the balloon, these balloons fall back down to Earth, and we recover the payload. The second type of balloon that I mentioned are called picoballoons, and these are, once again, very small balloons, but they work on the principle of being superpressure balloons. And what that means is, instead of the normal traditional latex balloons that go up and up and up and pop, these balloons instead are filled very slightly, just enough so they're barely lifting off the ground, and they ascend into the sky until the material that they're composed of physically resists expanding anymore. And at that point, the volume of the balloon becomes constant, which then allows the entire balloon system, so the balloon and the payload, to reach an equilibrium where the force of gravity pulling on the balloon, pulling it down, becomes equal to the force of the fluid it displaces, so the buoyant force. And at that point, the balloon stops ascending, it stops descending, and it just floats at that altitude like a boat on water. And it can stay at this altitude for days, weeks, and months at a time. And it's all because of the polymer. Unlike the latex balloons, which are very stretchy, these balloons are made out of two types of polymers. Either they have a metallized polymer, which is, you probably know it as mylar, or scientifically called biaxially oriented polyethylene terephthalate. And the second type are called non-metallized balloons. And these balloons are made out of a complex polymer layering system, where about 7 different types of polymers are layered on top of each other to give a different qualities as compared to the metallized balloons. But overall, both types of these pico balloons are very resistant to stretching, and they're still flexible, but they're like a quilt. You can move them around, but you can't stretch them or pull them apart like you would with a normal balloon. And in the picture you can see on the right, that's actually a friend of mine who went down to Antarctica to perform research with these pico balloons. And what he did was he went down there to show NASA that we can use these cheap balloons, which cost maybe $100, $200, to perform the same research that a balloon the size of this building could do at a cost of millions of dollars. And he was successful in his endeavor, and he used one of my balloons to send it around Antarctica, and it went around the South Pole about 8 times. and they went within about 108 miles of the South Pole. So these balloons are small, but they're mighty. Now going into the two different types of picoballoons, the metallized, as the name suggests, are metallic in appearance. These look exactly like the party balloons you'll see at the store. And the nice thing about them is that they have a high amount of solar reflectiveness. And what that means is, once they reach altitude, they're reflecting a lot of the sun. And so that allows for the internal gas within the balloon to not undergo extreme cycles of heating up and cooling down in the day-night cycle. And that causes the balloon to, instead of normally expanding and contracting as it heats up and as it cools down respectively, it instead stays at a relatively constant volume and ensures that the seams surrounding the balloon are sturdier and resist damage over time due to that expanding and contraction that you see with the normal, with the non-metallized balloons. And the non-metallized balloons, these are clear in appearance. They look like a laundromat bag. But since they don't have that reflective outer material, they have greater internal temperature change as they float through the sky. And so sometimes we see them losing helium or hydrogen, which are both the typical filling gases of these balloons, relatively quickly as compared to the normal metallized balloons. But the overall component that both these types of balloons share is that they have to be stretched before they're launched. And what that means is we fill them up with a bunch of air to stretch them out, like what I'm doing in that bottom right picture. And we do that just to make sure all the seams of the balloon are fully expanded, make sure the balloon is completely unfolded, and make sure that there's no stress points as the balloon expands on its actual flight. All right, so and a little history about HABs. So these are scientific in origin. So these high-altitude balloons go all the way back to about the 1700s, where the first Enlightenment scientists in France were using large hydrogen balloons to study weather patterns. And what they would often do is they would fill a massive hydrogen balloon, float up into the sky, write down what they saw, and then just kind of hope that they came back down. And one unique thing I found was that a French scientist, you sort of see in the bottom left picture, one of his experiments was getting on a horse inside of his gondola attached to his balloon and floating right into a thunderstorm. Now, surprisingly, he survived, even though his balloon was filled with a highly flammable gas in the middle of a highly dangerous thunderstorm. But he survived, the horse survived, scientists back then were doing some insane stuff. But eventually we come to 1902, where we see the first real scientific use of these high-altitude balloons being unmanned. And a scientist by the name of Leon Tesserink de Bort, he's a French scientist, so it's kind of hard to pronounce his name, launched a few unmanned hydrogen balloons with rudimentary meteorological equipment. And he left these balloons up in the sky for a couple days, and he was able to collect measurements. And these measurements were able to help discover what is called the tropopause in the atmosphere. And the tropopause is the point in the atmosphere which changes depending on where you are on the Earth's surface. And that point is where the temperature change starts increasing as you go up in altitude. So, yeah.
I'm sorry, folks, we're having some technical.
The projector is not behaving well.
So going back to the board, he used these balloons to help establish the tropopause, which is the point at which if you keep on going up in altitude, instead of the temperature decreasing, the temperature starts to increase due to solar radiation. And so traditionally, if you're ascending for some reason, it starts to get colder, but once you reach the tropopause, the atmosphere changes from being the troposphere, which is what we're in right now, to becoming the stratosphere. And at that point, at the tropopause, no storms can really go above that, except for some very rare circumstances. And because of that, we try to put these high altitude balloons, the picoballoons, above that line, the tropopause, to prevent them from being taken down by any of these storms. But from 1902, eventually in 1964, the first amateur radio HAB launch was performed by a couple of East Germans when they attached a small 250 megawatt transmitter to a hydrogen balloon, which is what this new newspaper clipping is. So say what you will about East Germany, but they had some enterprising young hams. And so ever since 1964, we've had great progress in high altitude balloons going all the way to today. Now, some of the payloads that these balloons can carry change greatly. So the pico balloon payloads, these balloons can only carry a light payload because the balloons are about this big. And so the payloads are about 10 to 20 grams in weight, and it's typically just a small little tracker, like what you see on the right. It's just 2 solar panels attached to a tiny little PCB. And for these payloads to communicate back with us, we use 2 types of communication protocols. On some trackers, we use APRS, or Automatic Packet Reporting System, working on 2 meters, and along with that, we also use WSPR, or Weak Signal Propagation Reporting Network. And for our balloons, I use 10, 15, and 20 meter WSPR, and using WSPR on the pico balloons gives us a huge advantage, because what can happen is as these balloons float across Earth, they can float over a place with no eye gates or no civilization, like the Sahara Desert, Siberia, the Atlantic Ocean. And if you're using APRS, which once again works on 2 meters, there's no eye gates to receive those transmissions. And so you kind of are in the dark, and the balloon can't talk to you when it's flying over these regions. But if you're using WSPR, like how we do on HF, then we can track these balloons pretty much for their entire journey, except for when it's dark out, because they can't power their batteries. So even if the balloon's flying over the middle of nowhere in the Pacific, we can still track it as it floats across the globe, because the HF waves bouncing off the ionosphere being able to be picked up across the globe. Now, for the traditional balloons, the latex balloons, as I said before, these can carry massive payloads. So for my balloons, they'll carry about 200 grams to 2 kilograms. But these payloads can become much heavier depending on the size of the balloon. So on the left, you'll see my friend. He's carrying the primary payload of a balloon that the Georgia Tech High Altitude Balloon Research Group launched, and I believe their total payload weighed about 15 pounds. But since these balloons carry a bunch of stuff, they can carry biological samples like crickets, nematodes, as well as stuff like amateur radio trackers, Geiger counters sometimes. We expect to recover these payloads because of the sensitive equipment that they carry. And so we equip these balloons with parachutes, and we typically have a great time finding these balloons. So sometimes recoveries go great, like they land in a field, like what you can see on the right when my sister recovered one of our HABs in a field next to a peanut processing plant. But sometimes the recoveries don't go so well, and on the left is a group of boys I helped launch their balloon with, and their balloon fell right into the woods near the Georgia State Cemetery up in Canton, if you know where that is. So luckily it did not fall into the cemetery, but it fell nearby, and they had to take a trek through the woods to try to find them. Now, the main purpose of all this, of my participation in high altitude balloons, is really to bring youth into amateur radio. So one of these events that I've done with students was a launch at Lilburn Elementary School down in Gwinnett County. And I brought one of these small picoballoons to there to help teach the kids about basic things about buoyancy, amateur radio, and whatnot. And the kids knew an incredibly high amount about amateur radio. The students were asking stuff about, what wavelength these trackers work on, how are we able to track them as they go across the globe. And the primary reason why is because GARS, Gwinnett Amateur Radio Society, actually works with these students. They set up a radio station there, and I was just amazed at how well these kids were able to latch onto these topics and really learn them and practice them as well. Because later on, after that presentation I did with the students, we launched one of the picoballoons, which you can see in the middle, and the kids were having a great time fighting over who would be able to launch the balloon, and they were having such a great time doing that they accidentally let it go. And so on the right you can see the balloon flying away. Now sadly, the balloon didn't go too far. We started tracking it when it was approaching Athens. And here is the complete path of the balloon on APRS.FI. This balloon was working on 2 meters. And we started tracking it near Athens. We went about southeast towards South Carolina. And once it went over the border, it disappeared. So there might have been a storm down there. Maybe the South Carolinians didn't like us. I don't know. But even though the balloon's journey wasn't too eventful, what was most important was that the kids had a great time doing this. They learned a whole lot about balloons, about buoyancy, and were able to explore an area of amateur radio that they never thought of before. And actually, right after this, the teachers wanted me to come back to see the students again and to have a demonstration to the whole school about high altitude balloons. Now, next up is YOTA Camp, or Youth on the Air Camp. And what YOTA Camp is, it's an event to keep youth in amateur radio. Because a big issue that we're seeing in amateur radio is not necessarily bringing youth in, but losing them. Because what happens is kids learn about them or learn about amateur radio from their parents, but once they leave school or once they leave home to go to college, they just forget about it and they don't care about it anymore. And so what YOTA Camp is a way to keep kids in amateur radio through involvement in STEM and amateur radio. And we do this by providing cheap and easy ways for students to get into amateur radio, to participate in it, and also to explore different avenues. So those might be high altitude balloons, satellites, circuit design, basic soldering, and a lot of times these kids' first HF contact is at a YOTA camp. So these camps provide a great way for youth ages 15 and 25 to access amateur radio and to learn something new about it. Now, this year, YOTA Camp was held in Denver, Colorado, in a suburb of Denver called Thornton. And for my session, I was launching 2 picoballoons and then 1 traditional latex balloon. And all 3 of those balloons were supported and helped through the generous donation and contributions from NARFAL. And the primary goal of these balloon launches was engagement with the youth. We wanted the kids to be the ones preparing the balloons, setting them up, balancing the balloons, attaching the payloads, and actually letting the balloons go. And during the whole time, I made sure that the students were the ones in charge, the ones really leading it, and I was just the one standing on the sidelines, just helping teach them what to do and when to do it. So for the latex launch, we had a pretty large payload. We had GPS trackers, we had weather instruments, we had an APRS sky tracker with my father's call sign W4SDR-12, and then we also had an ADSB beacon and a cutoff system. And what the cutoff system is when the balloon pops, once it reaches about 97,000 feet, the cutoff system cuts the balloon away from the rest of the payload system to ensure that the balloon doesn't get caught up in the parachute and potentially leading to the payload to fall and get damaged because the parachute didn't successfully deploy. Now, the highest altitude reached by this balloon was 97,000 feet, which is actually kind of low for my past balloon launches. And what's also surprising is we use hydrogen in this balloon rather than helium. And because hydrogen is a less dense gas compared to helium, we expected it to go a little bit higher than normal, but instead we didn't get that for whatever reason. So, So here is and along with the payload, yeah.
All right, good morning. It is June 16th, 2025.
I'll just skip the video. But along with the normal payload that we had a voice beacon attached to it that transmitted my call sign as well as a short message telling those listening on 2 meters to go to aprs.fi and to look up the call sign and to listen to my voice beacon. And so on what you can see right here is a chain of my payload. So on the bottom you can see a bright orange box. That is the voice beacon right there. It was a little Arduino attached to a bow thing that had that transmission cycle going. And then attached to it in that red pouch was the APRS sky tracker, then a camera, the ADS-B beacon, and then another GPS tracker, and then the parachute. So there were all the kids out in a drainage pit getting ready to launch a balloon, and it went off without a hitch. And along with that launch, we also we also had the picoballoon launches. Now the picoballoon launches, instead of occurring at the campsite, they occurred at WWV with the National Institute of Science and Technology. So it was a good bit outside of Denver, it was in Fort Collins. But the kids were able to go out to the transmission site and were able to launch the balloon somehow with the permission of the technicians there. Now, thankfully, the balloon did not go into any of the radio towers there. Instead, the balloons went almost entirely around the world. So I'll show you the launch footage of the second balloon that we launched there.
You can comment through the video since we don't have.
Oh yeah. So there the balloon goes. And as you can see, the balloon is ascending very slowly, and that's just because we want to put as little gas in the balloon as possible to allow for it to expand more and to reach a higher altitude. And off it goes. And you can see just how small the payload is attached to the bottom of the balloon. Now, going back to the latex balloon launch, we were able to capture this footage from one of the cameras on board. So this is when the balloon was at about 85,000 feet, so it was still rising. And you can see the blackness of space, you can see the curvature of the Earth, and if you can sort of see on the right here, that little gray speck is the moon. So you can see some beautiful shots just from a cheap little balloon. Now, we recovered the balloon pretty easily. Here is the journey of the balloon. So we launched it in Thornton, Colorado. It went northeast, and thankfully it avoided the Denver International Airport, which is a big concern for us. But it went east, it made a huge loop, went west, and then popped, and then it made another loop again, and then started heading east until it popped at the top right there. And that straight line you see on top, and then going left, that's just from my dad getting the payload and driving back with it. But surprisingly, it landed right in a field, right in a big old wheat field, no trees. We're close to it, and you can see the parachute on the top right picture, and there is the voice beacon box with the Norfall sticker barely holding on. Now, going back to the picoballoon launches, we launched 2 balloons. As I said before, both of them had a similar call sign, both different SSIDs, W0 Yankee-1 and W0 Yankee-11. One was on 10 meters, the other one was on 15 meters, both using Whisper, and we launched them at WWV, and both of them had great journeys. Whiskey 0 Yankee-1 died or was possibly shot down when it went over the border of Iraq and Iran. And Whiskey 0 Yankee-11 almost made it around the entire world. It went east, it went towards Spain, Portugal, went over Europe, I believe over the Middle East, and it finally went all the way around towards Hawaii, to Washington, and eventually when it was over Utah, it disappeared. So we almost made it around the entire world, but sadly it was a little bit short. So here are the campers that are helping assemble the payload on the I think this is the first balloon. So they're putting it together, they're holding the balloon, they were the ones that decided when to launch it, and on the right are the two balloons that we used for the launches. And as you can see, these are the metallized Mylar balloons, and they performed excellently. We had no issues with them, and the campers had a blast doing this. And here's some pictures of WWV, of the control center, and on the right you can see all of the radio towers we were able to miss with the balloon. And transition there. And there's some footage, a picture from the launch. And then here are the paths of the first balloon, Whiskey Zero Yankee -1. So it made it over the Atlantic. It went east over Algeria, Tunisia, Libya. It went towards the Middle East, going over Turkey. But as you can see, once it went over Iraq and started to go into Iran, it stopped transmitting right when it made it over the border. Now you can see the altitude's kind of low at about 4,000 feet, so it might have just iced up and lost altitude, or it might have just been shot or something and it just had a slow fall. But overall, though, it was a great path through the balloon. And for the second balloon, Whiskey Zero Yankee -11, here's it made it over Hawaii and then went east towards Washington and came down south. And eventually, once it went over Great Salt Lake, it disappeared. But both balloons, they're widely successful because the thing is, a lot of times when we launch these balloons, especially here in Georgia, they typically get caught in some storm off the coast. And so launching them in Colorado was a huge blessing for us because we were able to get them up to altitude before they could hit any major coastal storms. And I think that was the primary reason why we were able to have such a success with these balloons. So thanks to NARFL for the support, and I hope you enjoyed the presentation. Thanks.
Steve, yeah.
We got a question there.
Yeah.
All right.
Who's got a question?
Yeah.
You'd mentioned ADS-B, that's the automatic I forget what it is, but it's supposed to be notifying aircraft, correct?
Yes.
So I've seen many presentations. No presentation I've ever seen included a comment about ADS-B. So do you get a registered beacon and you're able to put it on the payload? How does that, what's the protocol for doing that?
So we did the HAB, the latex launch with another group called Edge Space Sciences, and they provided the ADS-B beacon. And since we were working with them, they had a requirement that they had to have an ADS-B beacon on board. Now, going through the process of putting one on a balloon, I believe they bought one, they packaged it up, and they programmed it to have their call sign on board. But if you ever go into a flight radar, you probably will see like some balloons have them. It's not a requirement. It's definitely not something that everyone needs, but it just adds an extra sense of safety, especially if you're launching near airports, like what we were. So, is it required? No, but it can definitely be helpful sometimes.
Thank you. Hang on a second, we got another one.
Hang on, Joel.
Jack, you talk about using helium versus hydrogen in the balloons. If you use hydrogen as your lift agent, do you have to take any special precautions to deal with the flammability for safety?
Not really. We have a fire extinguisher nearby, but the biggest precautions we have are just prevention. Making sure no one's smoking nearby, there's no open flame. But even then, the biggest hurdle with dealing with hydrogen is insurance. Like if I'm doing a school launch, a lot of times if there is insurance involved, they'll shy away if they hear hydrogen because they immediately think of the Hindenburg disaster. So we just have to tell people, no, the balloon's not going to blow up and burst into flames and everyone's going to catch on fire. And we just tell them that even if it did detonate, it would be a puff of smoke. And the flammability risk to others is very low, especially with the size of these balloons.
Thank you.
When you are near an airport, how far away do you have to be to keep the FAA happy And do you have to notify, get a NOTAM issued for pilots flying in the area?
Yes, so when we launch the large latex balloons that go way high up into the sky, we do get a NOTAM. And if we're launching by an airport like what we're doing, we did contact the airport as well as FAA just to tell them what we're doing, the possibility of a balloon flying into the airspace of Denver International Airport. But for the smaller picoballoons, we do not get NOTAMs. And the reason why is, there's never been really any contact with picoballoons and the aircraft yet. There was one incident in Russia where a weather station launched a large latex balloon right when an aircraft was taking off, and so the balloon got sucked into the engine and the plane crashed. But luckily we're not doing that, we're not that stupid. So we just try to be wise, and even if one of the small picoballoons were to make contact with an aircraft, it would either just be completely incinerated or just brushed off because their weight is so small, they pose no threat to aircraft. Yes.
You've done a number of launches over the years. How many around the world launches have you had? And also, I'm presuming there's some sort of ID on there for, like, if it goes down in a field someplace, it's got something that the farmer or somebody can get back to you.
Yes, we do have an email address on there, and that's about it. The amount of cross global launches that I have, probably about, I'd say 4. It definitely is hard to get a round the world balloon path, and really the ways to do so are launch at night when wind is low. To launch inland, so Colorado is a great example. With us launching not near some major body of water or near a coast, that gave us a huge advantage to prevent us from going to a large storm. Because what happens is when we launch here in Georgia, all of our balloons get pushed down towards Savannah, and if you especially do launch it during the day, they get caught in some big storm or hurricane off the coast, and a lot of times we just lose them pretty easily. So launch it during the night and launch it way inland.
So in terms of launching it inland, you mentioned like Colorado. Is that because you can get altitude based on Coriolis effect kicking it out?
Yeah, I mean, if you're launching here in the South, I'd say launching in like Tennessee, North Carolina, somewhere close like that can help you. The Coriolis effect, I mean, launching in Colorado, I just use that example because I did it with YOTA, because pretty much all my balloon launches have been in Georgia, not outside the state. But I think even if you launched it in an eastern inland state like Kentucky, I think you would still be fine. I think you'd still have time to reach altitude before hitting the coast.
Yeah, this is a kind of big picture question. I mean, over time, you've had a lot of experience with these balloon launches. Do you guys at this point have a documented template or plan that you use going forward? I mean, check what you're going to do and the responsibilities for that project, FAA, for example. Do you have that kind of thing in place?
So we have an equipment plan, so we have a list of all equipment that's needed, steps that need to be taken. Concerning the FAA and other regulatory information, that's a case-by-case basis. And the reason why is because in Georgia, our laws concerning balloons are pretty lax, but if you were to go to a state like Virginia, if I was to launch there, that would be illegal because I'm above the age of 15. And what the law says in Virginia is if you're 15 or under, you can launch one of these balloons just fine, but if you're not a scientist or a government body, you cannot launch these balloons. In California, I can't launch the metallized balloons because they worry that they fall into a power line. In Hawaii, I can't launch them at all, and I think in Florida, you can't launch these balloons at all unless you're under the age of 2, because I guess they assume a kid like releases this balloon. So it's a case-by-case basis, but in Georgia, for the most part, regulatory steps I take are pretty low. It's only if I have to get a NOTAM issued for one of the larger balloons.
Well, thank you very much, Jack.
Yeah.
I'll just make a, yeah, give Jack a hand because this is impressive stuff. We got a little certificate for you too, as soon as we get our photographer up there.
I knew you could do the presentation. I didn't think you could do it without many interruptions. So, talk about tenacity.
Yeah.
You got it. Thank you. It was a wonderful presentation.
Happy to be here. Thank you.
And just a quick note, believe it or not, just like we got an acclamation from, or a proclamation from Governor Kemp this year about Field Day, and did that for all the amateurs, radio operators in the state. He also did a proclamation for Balloon Day in the state of Georgia, so you can go look that up if you want. So we might do something with Radio Balloon Day someday, you never know. All right, again, thank you very much. Thank you, Jack. Thank you to the AV team for doing what they were doing tonight. I'm not sure what it was, but it was magic. There you go. Just like radio.